Hello, everyone. My name is Simone Severini, and I am the director of the quantum computing team at Amazon. I'm joined today by six of my colleagues to discuss the field of quantum computing, how they got started in the field, and what's to come in the future. Thanks for joining all. So I want to start our conversation by getting grounded on all your origin stories. So tell me more about your career path and what led you to pursuing the field of quantum computing.
So maybe I can start, Simone.
Please.
So if I trace things back, right, with the benefit of hindsight, my interest really started as a kid. I was very interested in mathematics and reading little things. And I read about these things called trapdoor functions, which are operations that are very hard to do in one direction, but very easy in another direction. And I read about it. It was super cool. And I forgot about it. Then I went on to do a degree in physics. And eventually when I was doing a postgraduate, I read about this thing called Shor's algorithm, which has an intimate connection to these trapdoor functions. And I thought, oh, that is really, really cool. But I really liked optics. So I went on to do a postgraduate in optics. And then I heard about this thing called quantum key distribution that really tied in together all my interests between mathematics and security and physics and optics. And I knew really that I had found my path. And since then, I did a PhD in Oxford making entanglement sources. And I moved to Santa Barbara. Then I went on to start something in Singapore, and eventually I ended up here in AWS.
So where did you read about trapdoor functions?
Oh, so Scientific American used to have these little mathematical puzzles column. I can't remember what it was called, but they had this a guy called Martin Gardner that published these things, and these things got compiled. I mean, this was before my time, but they got compiled into books, and one of these books was lying around in my house, and I devoured those things. So
right,
that was it.
Earl, tell us about your interest in quantum computing, please.
Thanks, Simone. So as a kid, I grew up on a mix of programming a ZX Spectrum, playing lots of Dungeons and Dragons and doing nerdy things like watching too much science fiction. And for me, that kind of like mixture of science, technology, and magical thinking seemed to lead me to doing a degree at Bristol in physics and philosophy. And then throughout my degree at Bristol, quantum physics was by far the most fascinating subject, both on the physics side, but also on the philosophy side. But then after the end, when it came to the end of my degree, I kind of thought I wanted to carry on exploring this weird world of quantum physics, but I also wanted to do something practical that would have an impact on technology and to kind of revive and reconnect with this childhood interest I had in computers. And so quantum computing was the obvious choice.
Right. So you see, it's interesting that Antia interest in science started from reading some more computer science related material. Your interest in science also was related to computers in a way because you were playing with Spectrum as a kid. So I guess that John interest in quantum computing instead came from a different direction. John, right? Started from physics directly.
Well, that's right, Simone. I started my career in elementary particle physics, and I worked on that for 20 years. But I changed direction in the mid-1990s when I heard that, at least theoretically, a quantum computer can find the prime factors of a large number. That's a problem we think is just too hard with the computers we have today. And the idea that problems that would otherwise be too hard to solve can become easy if we take advantage of abstruse laws of physics, that really fascinated me, and I still feel that way. And since then, I've been excited about quantum information science, both because we're laying foundations for revolutionary technologies and also because we're opening new opportunities to advance physical science. So I'm still a professor at Caltech, where I've been on the faculty for 38 years now, but now I'm also an Amazon Scholar affiliated with the Center for Quantum Computing that AWS recently launched on the Caltech campus.
Yeah, so you started reading about quantum computing after you have seen Peter Shor article, and it seems that both you and Antia started looking into quantum because of Peter Shor. I actually started looking into quantum because of you, John, because I was learning quantum computing in your lecture notes back in 1998. So yeah, it's science is interesting. There is, as you say, standing on the shoulders of giants, but also giving each other's hand and in a chain of people connected with each other. James, what about you?
Yeah, so I grew up outside of DC. I think for me, my interest in quantum computing came about from just I went to PhD and my advisor gave me Nielsen and Chuang's textbook and said, read this over the summer. And then I just cut in, and it was a lot of fun. I think for me, my interest in quantum computing and computing generally started with my dad's hobby interest in computers. And I was programming in BASIC when I was in middle school. So it was a lot of really fun things to just play around with. And I think for me, quantum computing really came about as a really interesting synthesis of a lot of ideas, because I had learned chemistry and then I had learned mathematics, and then kind of realizing group theory was the best way to understand a lot of things, really opened a door to really understanding a lot of things from a mathematical point of view. And quantum computing has been fantastic with the number of different areas that you can explore and go into and see the different branches. And so it's been really, really exciting to be working in this intersection of these different fields. And since 2016, I've been a faculty member at Dartmouth, and now I'm at Amazon visiting academic, where I'm able to build on this quantum educational experience that people are coming to Brockett, to Amazon Brockett to learn.
Yeah, and I guess we will talk about Amazon Bracket later during this conversation. So thanks, James. Katharine.
Yeah, so I went to the University of Waterloo for my undergraduate studies, which at the time and still is a very strong center for quantum computing. So as an undergrad, I took several courses in quantum mechanics, and then also they had a very nice course in quantum information that I took as an undergrad, and I had the opportunity to do an undergraduate research experience. And when I submitted the proposal for that, you had to offer two options with different professors. So I offered one in quantum information and one in condensed matter. And I ended up actually picking the condensed matter option and went to graduate school for that. So my graduate studies were mostly focused on computational condensed matter. And after a long detour in that area, sort of during my postdoc and now at Amazon Bracket, I kind of returned after a long time away to studying quantum information, sort of through the shared connections with computational condensed matter and tensor networks.
So interesting. When were you in Waterloo?
So I was there from 2008 to 2012.
So we overlapped because I was a postdoc in Waterloo. So Helmut, please.
Yeah, I think I probably have the most non-traditional path to quantum computing. I loved chemistry as a kid, and actually set my room on fire once, and to the dismay of my parents. But once I discovered physics in school, I forgot about chemistry completely, and was fascinated by how you can understand things in different ways and describe how different things happen in nature. And so I went to college, studied physics. Then basically was mostly focused on paper and pencil theory. And to my dismay, my parents never let me buy a computer as a kid. They thought it was a waste of money. And so I never really used a computer until I was in college, and then decided that, okay, this programming thing seems interesting, but I'd rather stick to math. So then once I got my master's in Switzerland, I decided to do a PhD in computational physics without actually knowing how to properly program. And that was an extremely steep learning curve, but I got fascinated by really hard combinatorial problems in physics, also known as spin glasses, and did a lot of very traditional classical statistical physics over many years, although here and there I would apply it to quantum phenomena, like, for example, topological color codes or any kind of topological error codes to compute the error thresholds. And then this was about the time also when the first quantum devices started coming online with promises of being able to solve these hard problems. And so basically like that, I slipped into quantum computing, just trying to understand these systems better. And today I'm here at Amazon, basically working closely with our customers, trying to solve really hard problems using quantum technologies.
Thank
What
you.
about you, Simone?
About me, well, I studied philosophy, so I'm an imposter here. So, but I ended up in quantum computing as well. But it's very interesting to hear these different stories. There are many ways, I suppose, to reach a point in an area which maybe is very different from the area where we started when we were undergrads, or some of you got interested in quantum computing because they were interested in computers. Some of you got interested in quantum computing because they were interested in physics, and so on. This is beautiful, right? And I believe that quantum computing is a fascinating topic also because it's so much interdisciplinary and puts together so many different areas and so many different people, and it's really exciting and fascinating. And you see, we read about quantum computers every other day in the news today, right? And there's lots of talking about quantum computing. But I think that an important question that I want to ask to the room is what is quantum computing? What are quantum computers? And please also explain me what it isn't. And I'd start with James.
Great. For me, for the way I like to think of quantum computing is that it's a new form of technology where you can leverage quantum resources to do computation. This is in contrast to semiconductor technology and standard forms of computation where you have classical bits and ordinary bits that behave under certain type of physics. And then when we have quantum physics, that we are enabled to access more degrees of freedom, coherent quantum variables, and this allows us to capitalize on the quantum coherence of these devices. It's important to recognize that this is not a silver bullet and not everything can be solved with quantum resources, but it does open the door to solving some very fascinating problems like has been already mentioned, Schwartz factoring problem and some combinatorial problems possibly. But I think this is really the exciting part, is to really see what can we do with this new form of technology that allows us to take advantage of quantum coherence.
Right, it's interesting. So quantum computer is a computer, but also is a device that helps us in the discovery process, almost like a telescope that allow us to see farther. Jonah, I'd love to hear your perspective on this.
Well, the way I look at it is, in the 20th century, we learned that at a truly fundamental level, all matter is governed by quantum theory, and that has already led to technological breakthroughs like lasers and magnetic resonance imaging and integrated circuits with billions of transistors. But really, those technologies are only scratching the surface of how quantum theory has altered our view of what's possible in the universe. When we have a system of many particles or many quantum bits interacting strongly with one another quantum mechanically, that's an enormously complex system. It's way too complex to even describe using the ordinary language that our computers today understand. And what a quantum computer will do is control and exploit that complexity. And that will enable us to process information in a completely new, more powerful way than we've ever been able to before. But quantum computing is so foreign to ordinary experience, we really have a very limited ability to foresee what the long-term implications might be. We can be confident, though, I think, that they're going to be very profound.
So, but then how might quantum computing be used in the future?
Well, this is the big open question. I think we're not sure about that. What we most clearly foresee is that we'll use quantum computers to solve quantum problems, to understand how matter behaves. That'll be important in applications to chemistry and materials, and that's going to benefit humankind in many ways. But very likely the most significant applications of quantum computing are ones we just haven't been able to conceive of yet, because it's such a different technology than we've ever had before.
It's a very beautiful perspective, yeah. And so obviously building quantum computers is challenging, right? And but why it is so difficult to build quantum computers, and how can you solve this challenge?
Is that one for me? Okay. Well, I think there are
Yeah,
really
or
two.
anyone else. I mean, you can start, John, and then let's see what the room has to say. Yeah.
Well, there are really two huge open questions. One is, how are we going to scale up the quantum computers we have today to much larger systems that can solve those really hard problems? And once we've done so, what'll be the best way to exploit the power of those quantum computing systems? And those are both wide open questions. These are not engineering problems. We really need advances in basic science to make progress. Now, you asked, why is it so hard? And I think an important part of the answer is that there's something fundamentally different about information in a quantum system than in a classical system like we use today. And that is that whenever a quantum system is observed, it's unavoidably disturbed in some uncontrollable way. So if we're going to process quantum information, as we will in a quantum computer, we need to keep it almost perfectly isolated from the outside world so it doesn't suffer that disturbance. And that's possible, but it's extremely difficult. And as time goes by, we're getting better and better at that. But, it's far from certain what the timescale will be for reaching quantum computers that will broadly benefit society, because we have such hard problems to solve.
So that's very interesting. And a question for Earl. We read often about the importance of correcting errors in quantum computers. I wonder if you could tell me a little bit about this.
Yeah, so quantum computers are very prone to noise because the components that they're made out of, the individual qubits, are always interacting with their environments. And so this creates errors in the system. And if we don't do anything about those errors, then the output of our quantum computer won't be reliable. So quantum error correction is a way of taking those qubits and turning them into a logical qubit. So a logical qubit is something that's built out of many, many physical qubits and is protected against noise. And I think the really kind of miraculous thing that also goes back to Peter Shaw in the 90s is that error correction is even possible. And I think it's kind of surprising that error correction is even possible, because you can't clone a quantum bit. You can't clone a piece of quantum information. And this is one of the underpinning reasons for why quantum key distribution works. So you can't clone information, so you can't make many copies of it and rely on the fact that if you lose one of the copies, the other ones are still there. So you have to do something smarter than that. And that's one of the reasons why I think quantum error correction is quite surprising that it even works.
It's fascinating topic. And now I've, of course, a very silly question is, will I ever have a quantum computer in my phone?
So maybe I can give it a go, since I'm an experimentalist. So I think everybody that is mildly interested in this topic has seen the pictures of the quantum computers that people have. So typically you see this sort of steampunk style chandelier hanging from the ceiling and a bunch of physicists working around it. And when you see that, that is the inside of what we call a dilution refrigerator, which is an amazing device that allows you to get to incredibly low temperatures. The reason we want the quantum computer, the chip, to be at these low temperatures goes back to what Earl and John were saying about error correction and the need to isolate these quantum systems from the environment. One of the best ways of isolating from the environment is just reducing the temperature. But when you see the size of these devices, of these fridges that we put the computer in, and all the things that are built around it, it's really hard to imagine that we would ever be able to put this in a phone or something that we can carry around. And as an experimentalist and somebody who has worked with these things, I myself find it very hard to conceive. Having said that, I am, if you've seen the pictures of the first transistors that people developed at Bell Labs and so on, they were also not in any way compact, and they were perceived as incredibly complex at the time. Like the amount of control that people needed to have on the impurities, on the materials and so on was amazing, was really challenging at the time. So I would say no. I would find it very hard to think of these things in our phone, but I would keep an open mind because we've fallen into that trap before. And also another point to make is that some quantum technologies, so not quantum computing, but some other quantum technologies such as quantum random number generator, so essentially exploiting the fundamental randomness that we have in quantum mechanics to generate high quality quantum random numbers, is already integrated in chips and in phones specifically. So, maybe we're not maybe it's not completely science fiction to think of these technologies being integrated at some point.
That's interesting. James, what's your take?
I think it's a really interesting kind of picking back off of that answer. I think with our phones, I mean, one of the things I've tried to do on my computer is to take software off of it, in the sense that I don't have the same build environment on my computer. Instead, what I do is everything on the cloud, right? I mean, this is the entire idea of AWS, right? Is that we don't need to host anything locally. And I think with quantum computing, we might not want it in our pocket. Instead, we want it cloud accessible, which is how it is now. And I think there's a lot of opportunities to put more things on the cloud and have less things on our phone. It's just a connection to other devices. So I think there might be a move away from it where you might have some quantum devices in your pocket, but I think it'd be more likely to have everything cloud accessible, including the regular devices. So.
But it's still, I from what I learned during this conversation is that it's so early for quantum computers, still a lot of uncertainty, and quantum computers most probably will have some surprises for us that we can't even imagine at the moment. And this is fascinating. And this is how science works, I guess, that it's very hard to predict the future, and the future may have some surprises that are beyond our imagination as well. This is quite a fascinating conversation. What I would like to talk about is you folks are working in quantum computing at Amazon Web Services. What is AWS doing to help customers with quantum computing, with their quantum computing needs?
So maybe I can start. So like I mentioned earlier, I work on the Amazon Bracket team. I am an applied scientist there. So what Bracket is doing is trying to create a sort of framework or tool set so that anybody who has an internet connection can access some of the leading tools in quantum computing. So previously, it used to be that, for example, if you wanted to try out a new experimental system, you really had to know and have a relationship with the PI of the lab who was developing that system. And of course, these people are very brilliant. They're very kind people. They love to collaborate with others. But if you don't already have a relationship with that person, it could be hard to start a collaboration. But now, since we're providing access to a variety of different emerging hardware technologies in the cloud, anybody on Earth who has an AWS account can run their circuit or their experiment on a cutting edge quantum device. And we also provide a suite of managed simulators and also a local simulator. So if you're doing something like algorithm development, or you want to try out a new idea for an experiment before you run it on a real quantum device, you can use a simulator that we've built that's very high performance and runs in the cloud. So these simulators simulate the execution of a quantum computer on classical hardware before you necessarily want to try it out on a real quantum device. And that lets you understand, for example, like how your algorithm would perform in an ideal case with or without the presence of noise, and other considerations like that.
That's interesting. So, but these machines are early quantum computers, and from what I understand, it's going to take a while before quantum computers will impact problems that have commercial value. I'd like to learn more about what approach, what is AWS doing with respect to hardware, and how AWS is interacting with customers in quantum computing.
Mm-hmm. So Simone, I work at the AWS Center for Quantum Computing, and that's the part of AWS that's responsible for designing and building our own AWS quantum computing hardware. So the main hub for that activity is on the Caltech campus in Pasadena, with which we have a close collaboration. And so this kind of complements what Katharine was talking about, the AWS Bracket service, which is providing access to third-party hardware. This is going to be our own hardware that we're developing. But to kind of solve all of our customers' needs, we're going to need eventually to build a very large-scale quantum computer. And there are many scaling challenges that we're going to face. And while university research has brought us a long way, and indeed compared to my PhD days, I'm really amazed at the quality of qubits that you can get nowadays. But I think it's also clear that universities are not going to get us to the scale that we need to have a large-scale quantum computer. And so companies are now leading the way in developing large-scale devices with consistent qubit quality. And AWS is starting to bring its expertise in technology at scale.
Right. That's interesting. But so what I like of a service like Bracket is that it can offer a window over the state of the art of the technology. And since technology is still early days and there are many different ways to build quantum computers, I think that having the possibility of seeing different ways that are used to build quantum computers, it's interesting. It's interesting for a number of reasons. So Helmut, I wonder if you can add the perspective of how you interact with customers.
Sure. So let me tag on to what you just were saying, that Bracket offers a wide variety of devices. I think this is something very important because we can't just assume that one particular technology is going to work really well for a particular problem. And so having the ability to compare the performance of different devices on different problems is something that is very important at this stage. I don't think it's too early to start engaging with customers. I think it's, on the contrary, very important. And I agree with what John said earlier, that we still have to find the best possible applications for quantum devices. And for that, it's really key to work very closely with customers and their experts to try to analyze the big pain points and problems that they're trying to solve to see where quantum technologies can help them best. And so we have been working with our customers very actively in many different areas, be it, for example, in healthcare and life sciences, in chemistry, in finance. And we see a lot of problems that come mostly from the same areas. For example, optimization, for example, chemistry, for example, pharma, where you want to do basically chemistry on a smaller scale. And it's very clear that certain patterns are emerging that are also educating us as to where we're missing quantum algorithms. And this is something that is very important. We are focused very much on the hardware, but we also need to start thinking about what are the new algorithms we're going to develop such that we can better solve these problems. And for this, I think that having this whole process driven by our customers and trying to get them quantum ready at the same time is a very important way to go.
Right. So it's interesting. On one side, a challenge is to build a quantum computer. On the other side, a challenge is to articulate use cases and to design quantum algorithms that can actually run on the quantum computer. So.
And the thing is, you know, quantum is so weird and different that we cannot just take a run-of-the-mill problem and say, well, I'm going to run this now on a quantum computer because I knew how to do it on a classical computer. We have to take a step back and think how we're going to model this problem on a computer that has quantum effects driving it such that we can solve it. And that's a highly non-trivial task. And this is why Amazon has the Quantum Solutions Lab, where we work closely with our customers to try to take these real-world problems and then convert them into a form where they can be solved on quantum backends.
Right. It's interesting you say that you cannot just take a problem formulated in the way we formulate it traditionally for digital computers and just translate it for a quantum computer. There's a different process. That's interesting. So when I think about quantum computing today, and when I look at what is happening in quantum computing today, I see a lot of innovation across the board. I see innovation in startups, innovation in large corporations, and an enormous amount of innovation in academia. And I think that the role of academia is still central and fundamental. And I'm curious to know how Amazon is working together with academia to solve some of the challenges in quantum computing.
Yeah, so perhaps I can say something to start off with. So, as I mentioned earlier, the AWS Center for Quantum Computing has its main building on the Caltech campus. So there's certainly a close collaboration with academia through Caltech, but then we have various scholars from Caltech and other places. But also, quantum is growing very, very fast. And so there's a pipeline of students with the right skills that is really, really crucial to maintain the growth of the whole field. And so one of the ways I think that we can do that and support that growth is through the internship scheme that we have, which gives the kind of brightest and best PhD students a chance to work with us on building quantum hardware and thinking about what kinds of protocols and algorithms we should run on that hardware.
Just to follow up on the AWS Center for Quantum Computing at Caltech, I think that's a partnership that's very beneficial to both sides. Caltech has a thriving community of scholars working on quantum science, and it's very exciting for people at Caltech to have in our midst an industrial scale effort to solve some of the big technical problems that'll make quantum computing more powerful. And for the AWS employees who are embedded on our campus, it enriches their intellectual environment to be at a place that's aggressively advancing quantum science and technology across a broader front. I think that synergy makes everyone stronger.
So important, a good example of collaboration between academia and industry.
Right.
I can also chime in. Another interesting way that Amazon's engaging with academics is through a lot of the visiting scholar programs and Amazon Visiting Academics. I myself am visiting academic, which is aimed at pre-tenure, early tenure faculty, and it's been a fantastic way for me to kind of bridge between the academic setting and the industrial setting here at Amazon. So I think this is something that a number of us are actually have joint commitments between academia and Amazon. So I think it's another way that it's really engaging on a person-by-person basis rather than these large-scale collaborations as well.
Right. So a strong communication channel between academia and industry. And I think that this is fundamental in an area like quantum computing, an area where there is, of course, engineering problem, but also some fundamental science still to sort out. And what I get out of this conversation, the sentiment is that there is still a lot of uncertainty about quantum computing, but definitely it's an area that is moving fast and where there is a lot of innovation happening. And I'm curious to get your opinion about where do you see this field going, let's say, during the next 10 years?
Well, first of all, I would say nobody knows. But it's very likely that we'll have much more reliable hardware in 10 years. That's going to make the technology more powerful than it is today. But based on what we currently know, I think it's not particularly likely that even with substantial progress on the hardware, we'll be able to run the most impactful applications of quantum computing that we currently foresee, for example, to developing new materials or chemicals. That probably isn't going to be practical in 10 years. But I think it is likely that making use of this technology in the next 5 to 10 years will make new scientific discoveries, because we have tools now for exploring the behavior of complex quantum systems that have never been available before. And this is the way science often advances. You have new tools, new instruments, you can do new kinds of explorations, and you find new things.
Yeah, Simone, I myself, as I'm an experimentalist, so I'm always excited about the evolution of the hardware, but I really think that in the next 10 years, what I'm really watching and what I'm really excited about is watching a much wider range of people interacting with quantum computers. I think really, and this has happened in classical computing as well, right? People imagine applications from a high level, but then you get a wide range of people that are experts in completely different areas and start playing with the machines, trying little things, trying little algorithms. And just that exploration drives drives advances. Especially in this area that we're now with these quantum computers that are still relatively small, as John said, we think it's going to be a while until they can do something like run Shor's algorithm. But there's this huge intermediate space between being able to run Shor's algorithm and what we have now that is virtually unexplored, because the machines are not perfect. Sometimes they might have, early machines might have error correction that only corrects like some types of errors, and we just don't know what we will be able to do with these machines on the short scale, particularly as domain scientists, as experts on other completely disconnected areas of science start looking at these and appreciating or having insight into what these machines can do for them. So that's what I find super interesting, and I'm looking forward in the next 10 years or so.
Yeah, so as John said, it's hard to kind of look into your crystal ball and see the future. But if we kind of look back into the past, then what we see is that a decade ago, the quality of qubits was much, much lower, certainly much lower than the quality that was needed to really demonstrate error correction. And so for me, that's the most kind of exciting thing about the moment that we're at the moment, because we have reached this point where the quality of quantum computers is at that threshold at which you can expect to build a logical qubit, and for that logical qubit to be better than the individual physical qubits that you built it from. And so I think that's going to be the most interesting thing over the next decade. I think that we will see a logical qubit. I'm going to say that. I think we'll see a logical qubit that is better than a physical qubit. And I think we might even make a bit more progress beyond that. So we're going to make it many times better than a physical qubit. We're going to demonstrate some logical operations, and we're going to try and build further.
Yeah, but Earl, what is a logical qubit?
What is a logical qubit? Okay. Yeah, so a logical qubit is a qubit that's protected from noise. And as I kind of mentioned earlier, it's built out of lots of physical qubits. And so if I can kind of give a classical analog, if I say that I want to store the bit 0 or the bit 1, and instead of storing 0, I store the string 0, 0, 0, with each of those zeros stored in separate locations. And I store 1 as 1, 1, 1, with each of those 1s stored in separate locations. And if the information is damaged at any one of those locations, I can still retrieve the original message. And so that's classical error correction. And quantum error correction is kind of a quantum analog of that. I take my quantum state, and then I delocalize it across many physical qubits, across many different locations. And if I lose some small fraction of those, or only a small fraction of them are damaged, then I'll be able to reproduce the undamaged logical qubit. And so in a quantum computer, when we talk about a large-scale fault-tolerant quantum computer, we're constantly doing this through every single clock cycle, constantly refreshing the logical qubit.
Thank you. So, Katharine, I'm curious about your perspective on this.
Yeah, so I think my two main views for the future are kind of already covered, in the sense that it's super exciting that we now have such quality qubits that we can really start exploring the algorithms that have been discussed and developed like since the 90s, really. And it's a situation a little bit analogous to me to machine learning, where sort of like the fundamental algorithms that people use in machine learning were developed like quite a long time ago, even in some cases the 70s and 80s, but the quality of technology to run them on was not there. And then once the technology developed to the point where we could apply those algorithms, as probably everyone's aware, we saw like a real flowering of applications for machine learning, huge improvements in the algorithms we're able to use. So I'm excited for hopefully a similar process to occur with quantum computing. And then similarly, as we also know, there's been a huge growth in sort of the talent entering that field being machine learning, partly because we're able to now provide practical applications. There's a lot of opportunities for people to find good positions in that field. So I think the really exciting thing that hasn't already been mentioned for me is that we're going to see a new generation of students, professionals, if you will, like quantum engineers entering the field, who will be able to bring new insights that we haven't yet been able to imagine. So I'm really excited to see what sort of the quantum computing generation after us is going to be able to accomplish.
Yeah, quite interesting. And also, it must be said that quantum computing is just a portion of this larger, broader area, which is quantum technologies, right? And I'd be curious to hear a little bit about other quantum technologies in addition to quantum computing.
Simone, I'll take that because that's close to my heart since I've been working on other quantum technologies for quite a while. So as you said, there's quantum technologies. Broadly speaking, the field is called quantum information science, and quantum computing is one branch of that. It's maybe right now the better known branch, but there are other branches. So another branch is quantum sensing or quantum metrology. That is very active, and essentially it's using some of these quantum effects and maybe the more sophisticated quantum effects, so things based on some of the same techniques that we use in quantum computing, but to make things like better clocks or make sensors that are correlated to each other in interesting ways. And so people are doing a lot of developments for gravitometers and accelerometers and things like that, which have huge technical implications. The other area is quantum communications or quantum networking. And that is, I like to think about it as quantum computing being the stationary qubits and quantum communications dealing with the flying qubits. So just like in classical information, we have the computing resources and we have the communication resources. We have the same. We can map that onto what happens in quantum technologies. And it's been known for quite a while that we can do things in quantum communication that are pretty interesting. So one of the main applications is called quantum key distribution, where you can exploit the inherent randomness and the correlations that exist in quantum systems to create perfectly secure correlated numbers that can then be used for cryptography. So quantum key distribution, essentially you distribute secure keys between different parties. And that is really based on things like the quantum no cloning theorem that was mentioned before. So if you're transferring, if a qubit is going from A to B and somebody tries to measure it, it's going to inevitably disturb it in some way. And we can use quantum tools, we can use our knowledge of quantum systems to detect those interferences. Other really fun things are quantum teleportation, for example, where you can, it sounds like science fiction, but it's a real thing. We can transfer the exact quantum state from one location to another without signaling the contents of that quantum state in some sense. That's not a very good explanation, but really that is what's happening. And another thing that I already mentioned is, of course, these true random numbers or quantum random numbers. It turns out that randomness is an incredibly important resource in technologies. You know, people spend a lot of effort and money into generating perfectly random numbers and streams of randomness at high speeds. And that is something that quantum mechanics excels at. And we can do all sorts of interesting things. People have already integrated these techniques into chips, into phones, and that area is just growing very fast as well. So yeah, quantum technologies is lots of things, of which quantum computing is only a part. So we're very excited to look at all the implications of these technologies and how they connect to each other.
What do people do with randomness?
Yeah, good question. They do. So there are all sorts of applications for randomness. I can't remember who said this, but somebody said randomness is too important to leave to chance. So it does turn out that we need randomness for all sorts of things. On the maybe connecting to computing, we need randomness for things like Monte Carlo methods. So Monte Carlo methods are computational methods where you use randomness to sample from a distribution, for example. And I won't say anything else because I'll get it wrong and Helmut will go after me. But but that is a very important computational role of randomness. In security, randomness is extremely important. You use randomness every day. Your browser uses it to create short-lived cryptographic keys, to generate unique IDs, for example, to generate all sorts of things. So it's a very important technology, in fact.
Thank you. So suppose that I'm thinking about a career in quantum computing at Amazon. What words of wisdom do you have for me?
Well, of course, people from a wide variety of backgrounds can contribute to advancing quantum computing. That interdisciplinary character is part of why it's so exhilarating, as Simone and Antia have emphasized. There are roles for people who understand the hardware or the software or the applications and so on. If you don't have a background in quantum physics, I think it's very helpful to have some appreciation for the language spoken by quantum systems. It's different from the language that ordinary computers use. It's the language of a field of mathematics called linear algebra. And familiarity with the principles and methods of linear algebra, that's very empowering for anyone working in the quantum industry, and also a knowledge of probability. And those things are useful for other reasons too. But apart from that, my advice is, if you find quantum physics confusing or hard to understand, don't be discouraged by that. I've been a theoretical physicist for 45 years, and I'm getting confused all the time. That just comes with the territory. But just persevere, and a better understanding will come.
Thank you, John.
I can only second that, John. I only understood quantum really when I had to teach it at the university, to be really honest. I had no idea what I was doing as a student.
And probably even now, who was saying that if you claim to understand quantum mechanics, you actually haven't understood it? Was Feynman or?
It's supposed to be Bohr, I think, but who knows?
Bohr. Okay. even. Katharine.
Yeah, so I would also say, specifically for roles like mine, where on our team we work very closely with software engineers and people who are very smart and have a very strong background in classical computing but aren't necessarily quantum experts. It's very helpful to have some classical computational skills of your own. There's obviously a lot of room in this field for people who are focused more on pen and paper techniques. But day to day, I do a lot of coding on classical computers. So having sort of a mixed background in both quantum physics and just regular classical programming can be very helpful. It's useful to help understand what about quantum computing is surprising or odd if you already have a strong background in sort of classical computation. And the other thing that I think we've kind of been alluding to here is that since quantum computing is such a new area and it's very mathematical, it also helps to have strong communication skills to communicate with other people who have a strong technical background but maybe aren't quantum experts, or people who are interested in quantum computing in general, how it could affect their industry, their lives, but are not experts in physics or computation in general.
Right, and I guess communication skills is something related to all science, right? Because in science, you want to collaborate with other people, or you want to work with other people and with different skills, and being able to talk with people is important. And in science, 1 + 1 is always more than 2, right?
Yeah, I would build on what Katharine has said and say that, if you think of how, for example, what we're doing at AWS, you have this huge range. You go from building the hardware, where you need people that know about cryogenics and FPGA electronics for control, for example, then to physicists that are more on the superconductors, the theorists that help understand, the error correction protocols and how that interacts directly with the material systems and those controls. And then you keep moving towards the computational side, You have to look at the applications. So you need people that are domain experts on, say, biology, chemistry, operations research, all of these things. So sometimes people ask, what skills do I need to get into quantum computing? And I tend to think that a lot of it at this point is about combinations of skills. Do you know this and that, and can you make those connections? So I think there's a huge room for people who are curious and want to contribute to the field. Also, adding to what John says, I would say, if you want to understand what is weird about quantum systems, you need to understand statistics really well. Because a lot of it is in the correlations between systems. A lot of the surprising effects are about correlations. So maybe that's one skill I would say is very useful, something I would build upon.
Thank you, Antia.
So when I was, I guess when I came out of my undergraduate degree, I'd learned a lot of quantum physics, but I hadn't learned anything about quantum computing yet. And I decided that's what I wanted to go into. So I had a PhD interview scheduled, and I realized I had to very quickly learn something about quantum computing. So a few days before, I picked up a copy of some lecture notes by someone called John Preskill. I don't know if you've heard of him. Anyway, at the interview, I was asked many questions, which were exactly questions that came up from this set of lecture notes. So they were very helpful. I don't know if I would have actually passed my interview if it wasn't for those lecture notes. So highly recommend those for anyone that's starting out in quantum computing.
Thanks, Earl.
If I can just add a little bit at the end, I think or maybe not the end, but add a little bit more. I think one of the things that's been kind of underlined repeatedly throughout the conversation is how many roles there are and how the growth of the field, no one really knows where it's going to go, and this level of excitement around quantum computing that I think now is the time, if you're interested in the quantum computing, to go learn, to go explore, to go apply, to go see what you can do, see how you can build your skills into something that will be useful and contribute to the ongoing effort. I think it's a really exciting time. So I think my advice would be just go for it and try and skill yourself up in all the ways that everyone said already, but just, get to work and start.
Yeah, if I might tag on to that, James, quantum is different, quantum is weird, and the only way you're really going to get it is if you just play with it. And so I encourage everybody to just experiment, hop on Bracket, for example, and use the different backends. Try to come up with better ways of solving problems, because a lot of the innovation often happens at the intersection of different disciplines. And so having somebody come in that, say, is not an expert in quantum, but just starts experimenting, might unlock some of new solutions, applications, et cetera, that, we physicists or quantum researchers would not even have thought of, just because we're looking at everything always from the same angle. And so I think that, go play, roll up the sleeves, hands on keyboards, and get it going.
Interesting. So having an experimental approach to learning quantum computing, that's what you're saying. Yeah.
I mean, it's if I just may add to this, the last thing, it's like driving a car. You can't read a book and sit behind the wheel. You got to practice. And so it's the same thing here. Sit down, start coding up, interact with these devices, and see what you can do. Sorry for interrupting you, but
no. What I learned is quantum computing is a very interdisciplinary area, and it's very important, specifically because of this interdisciplinarity, that people that maybe have nothing to do with quantum computing itself get engaged and can contribute to the field itself, because they can bring a new perspective that maybe that people are working in the field do not necessarily have. Yeah. So, well, thank you. Thanks to my colleagues for joining and for this very thoughtful discussion. For those watching, make sure to check out our website, amazon.science, to learn more about quantum computing and other areas of customer-obsessed science at Amazon. And bye now.